this is the column, inverse fluidization column, which is shown to you earlier, and here is the distributor. Like ma'am told you earlier that there is a screen which protects the solid particles to move out from the perpex column. This is the perpex column, this is the mesh, this is the distributor, air distributor, this is the counter current flow reactor. So air will flow from downward to upward direction, and water will flow from upward to downward direction. The main difference is fluidized bed reactor and inverse fluidized bed reactor is the particle density. We are using a lighter density particle here, so that when we will fill the water in the perpex column, the particles will move upward using the buoyancy force. Then when the water will be filled into this perpex column, we will first measure its static height. When there will be no water is flowing inside the column, we will maintain the height of the particle, and we will record the static bed height HS. Then when we will again attain a steady state by controlling the inlet and outlet valve of the water flow rate, so that it will maintain a constant height. Then we will supply the air so that bubbling will happen. When bubbling will happen in this way, particle will get fluidized and it expand in downward direction. The highest expansion will be H max, the height which we will record, and the lowest expansion will be the H minimum, the minimum height the packed bed will expand. Now I am going to show you how the working is done in manner. First, valve is open. Now we will close it, and okay, sorry, I have not pump. You can see bubbling is taking place and water is flowing. Close the valve. Close it. पूरा close कर दो. हाँ ठीक अच्छे से स्टैटिक बेड हाइट नबा पे देखो छे. रुह तमे किसी से पूछ. As the lower density polypropylene balls of size 6 mm diameter and the 870 kg per meter cube densities. Now as we have filled water in the perplex column, now we can measure the static height, which is 35 minus 12, which is 23 centimeter. Now we will switch on the water flow rate, and we will calculate. We will see the flow rate here. This is the flow meter, digital flow meter. We will see the water flow rate here, and then we will attain a steady state by controlling this outlet valve and this inlet valve. Open. And pressure drop, and we have connected it with here in the column, where water up to which height the water is fixed. We have fixed it here, one here, and one end of the manometer here, so that we will calculate the pressure drop of the whole column. Then start. Now to attain the steady state of the flow inside the pot, and also outlet the water so that it maintain a steady state height. .1 flow rate nahi 0 अच्छी अटी करो. नब दिव्यांशु देखिए ठीक अच्छे we will write serial number, rotometer reading, H minimum, H max, H static height, manometer height 1, manometer height 2, and R and small r. This R and small r nothing but dimensionless number. R is equal to H max plus H minimum by 2 by H static height. R is a dimensionless number which indicates the greater expansion, suggesting the fluidization and mixing. It helps in determining the optimal operation parameter like fluid velocity. When R will be greater than 1, we will say that it is well fluidized, and when R is similar to 1, we will say that it is not a good fluidized or not fluidizing properly. R depends on the particle size and density and the fluid velocity. And small r is the ratio of H max to H minimum, which says the bed stability. When at higher R value, stability decreases as excessive expansion is there and particle entrainment will happen. At lower R value, we can see poor fluidization and insufficient particle suspension. So for R greater than 1, proper expansion of the bed will happen where the particles are fluidized and suspended in the liquid flow. टिके कमाओ दिव्यांशु टिके कमाओ position we have attained the steady state, and from here we can see the water flow rate, that is 0.5, and we will write it here in the table. And now we will pass on the air. Error of 0.5 only. Now from this compressed column, no constant bubbling, continuous man. से खोला स्लो बबलिंग हो किंतु टिके स्लो. No, this is not working actually. This is from that one. Bubbling is the air flow rate is high, with a high velocity air is flowing inside. Therefore vigorous fluidization is taking place. Fluidization here. That's why if we will pour water and we will pass air, it will burst out from the top, which has happened earlier also. That the air flow rate is at, now from the calculation we have stated that The air flow rate is at 18.9 meter cube per hour, and the H minimum H max का कहते थे 67 21. H max is 67 minus 21, that is 46 centimeter, and H minimum we will calculate 57 minus 33, that is 24 centimeter, and static bed height which was calculated earlier is 23 centimeter. Manometer reading Now from this value we will calculate the R and R. R is equal to H max, which is 46 plus 24 by 2 by 23, and small r is equal to 46 by 24. Solid hold up is nothing but the ratio of solid volume to the bed volume. Solid volume we will calculate by as solid volume is equal to 800 by 870, which earlier it was calculated 800 gram. The total bed weight is 800 gram, the polypropylene ball, and its density is 870 kg per meter cube. So by this we will calculate the solid volume, and by the bed volume as by 2 pi RL, by pi R square L, we will calculate the volume of the perpex column, the bed column. So and by this we will ratio it and calculate the solid hold up. And now coming to the static condition. In static condition, pressure drop is equal to A static into particle density minus density of fluid into gravitational force. Density of fluid is this. In the manometric fluid, in the manometer we have poured carbon tetrachloride whose density is 1.5867 into 10 to the power cube kg per meter cube. And when we increase in static condition, when we increase the fluid velocity, pressure drop also increases, reaching a maximum, which shows us the minimum fluidization velocity UMF. At this point, the drag force exerted by the fluid balances the weight of the particles. In the fully fluidized state, fluidization is achieved and delta P stabilization and become relatively constant. Beyond the fluidization, very high fluidization will occur and pressure drop will decrease. Now, after calculating from this table, first we will make this table in which water flow rate will be constant, and we will vary the air flow rate to take the hydrodynamic study, and then we will constant the air flow rate and take the water flow and vary the water flow rate. After that we will vary the packed bed height. Now the static bed height is 23 centimeter. We will remove some of the particles and maintain some height, so and by that we will make this third column, and after that we will plot a graph between delta p and u. Here in this graph, first when we increase the velocity of the air, the pressure drop increases steadily, and after increasing and this is called the UMF, minimum fluidization velocity, and after that we can see a constant pressure drop. And that's how we will take the hydrodynamic study of the inverse fluidization bed. And after that we will add, as we are treating the waste in inverse fluidization is widely known for treating wastewater. We are treating hexavalent chromium here. We will reduce it to trivalent chromium, as hexavalent chromium is carcinogenic for health and it has very health hazardous. So we will pour we have cultured the bacteria. We will show it now. We have cultured the bacteria. We have now cultured the pseudomonas bacteria. Then we will you can see here this one. This is the cultured bacteria, which actually we have cultured it, and we have stored it in the freeze. That's why they have settled down, and you can see the dense white color, which is nothing but our cultured bacteria. We take that and we will fill it here in the tank this side, and after going inside the Perpex column, they will form film above this polypropylene ball. Making film in above these polypropylene balls, they will contact with the chromium and reduce the chromium to trivalent chromium. And that's how the inverse fluidization works, and and why we are using it and how we are using it. Thank you. At first we have collected the chromite mine wastewater, as we are reducing the hexavalent chromium to trivalent chromium, and we have done a ICP-OS test where we found that the concentration of chromium is 3 ppm, and after the biofilm formation we will keep it for 3 weeks so that it will get the chromium will get reduced to trivalent chromium. And how we will know that the chromium concentration is reduced? We will use the UV spectroscopy. For that we will take sample from after 3 weeks. We will take samples in every 6 hour or 2 hour, and then we will check it in the UV spectrometer, where we can see the absorbance of chromium, and it will and we will can see that there from that we can see that the chromium, hexavalent chromium, is reduced to trivalent chromium by checking the chromium standard from the standard book, which for chromium we can calculate the absorbance of the above that what concentration has decreased in the hexavalent chromium. And we will also calculate this for the solid particles. We will collect the solid particles, and we have taken the BET analysis for that, and after that ESEM analysis for that, and after that we will, to confirm the growth of the microbe, we will see it, and it will show, like ma'am has shown you earlier, a dense particles film is formed above the polypropylene ball. Then we will take, which we, from ESEM we will be able to know that the film is formed successfully. Then we will pour it, then the reduction will also take place.
This is my three-phase fluidized photocatalytic reactor. Here, three-phase means we are using solid. Solid is our catalyst particle, that is CSGSC, titanium dioxide supported coconut shell granular activated carbon, and this is my solid phase. Now, liquid phase I am taking, normally for hydrodynamics purpose I am taking the water. For experimental purpose I am taking a dye solution. Now gas phase is what air, so compressed air, that is through filter medium you are giving compressed air or filtered air also you call. Now coming to the point, first of all you have to see the hydrodynamics, three-phase hydrodynamics, how it is occurring, hydrodynamic study. Now hydrodynamic study in the sense that here what are the hydrodynamic parameters. First of all you have to take hydrodynamic characteristics. What are the hydrodynamic characteristics you are reading? Now hydrodynamic characteristics in the sense that your bed pressure drop, from where you will get the minimum fluidization velocity. From this graph you will get minimum fluidization velocity. Now coming to the point, next hydrodynamic characteristic, that is bed porosity or bed expansion you are calling. Now in this you are calculating the bed expansion ratio, bed expansion ratio and your bed voidage. Now next one is gas hold up or phase hold up you are calling. Now these are the hydrodynamic characteristics. Now what are the operating variables? Operating variables you are taking here. The operating variables like liquid velocity or superficial liquid velocity you are calling, superficial liquid velocity, and superficial gas velocity or air velocity. Next our initial static bed height, and particle size. Then your our viscosity of liquid viscosity. Now these are the operating variables, these are the hydrodynamic parameter, and for various operating variable you are calculating the hydrodynamic, you are doing the hydrodynamic study of a three-phase fluidized photocatalytic reactor. Now here you are taking the annular shape in the sense that you are in the middle, you are making an annular region here. In the annular region you are taking the bed material. This is my annular fluidized bed. Now this is now for that what you have to do, suppose your bed pressure drop you have to find out, your effect of bed pressure drop you have to calculate. Now for that what you have to do, how to take the reading. You are reading what are, first of all you have to do the liquid flow rate. Different liquid flow rate or liquid flow rate. From the liquid flow rate you will calculate the velocity of the liquid. Now this is manometer reading. Here, this manometer reading, two limbs are there, left limb and right limb are there. And initially before changing the flow rate, at zero flow rate you will record the reading of the manometer. Then above that how much pressure drop is changing, that you have to calculate. Now this is manometer reading. Next you have to do observation you have to make, means what you are observing, how the particles are moving, how the particles are tilting, or no particle movement, only slight movement, that you have to record. Next, your liquid flow rate manometer reading, then your bed height. Bed height you have to measure. This is the, because from this table itself you have to calculate what are the effect of effect of bed effect of different operating variables on bed pressure drop, like by changing initially your gas flow rate you are keeping constant, you are changing the liquid flow rate, and remaining all the particles are remaining constant, like particle size, initial static bed height, all the things parameter will keep constant. Now when you will change the different gas velocity, you have to change the flow rate of the gas. Initially you are maintaining the constant flow rate, and for 0 flow rate then you will go for your 5 lpm to 10 lpm, like this different flow rate of air or gas you have to take into account. Now these are the different how to take the observation table in your hydrodynamic characteristics. Now from that you have to calculate the table and graphs, all these things which I have explained detail in the class. Now this is my hydrodynamic study. From this different for bed pressure drop we have done, like by changing various variables, like different hydrodynamic characteristics you can calculate by making the similar tables for different particle size for different initial static bed height. Now coming to the point, this is my how hydrodynamic study you are making. The basic of the hydrodynamic study already you know how terminal velocity will change, how the what is the fluidization generally. The fluidization particle means the particles behave like a fluid. Now here two-phase fluidization and three-phase fluidization, that different types of fluidization also you have seen, that particulate fluidization and bubbling fluidization. Here both mixing characteristic will get, because this is a three-phase fluidized bed. You are getting bubbling at 0 flow rate air flow rate, you will get in the particulate fluidization, and when you allow the flow of the gas, you will get the bubbling fluidized bed characteristic. Now coming to the point, photocatalysis. Now photocatalysis, this is the nowadays this is called also advanced oxidation process. Now advanced oxidation process now a burning topic, because maximally whatever the biological treatment or your adsorption experiment, what they'll simply transfer the material from liquid phase to the solid phase. Am I correct or not? From liquid phase to solid phase, because they are simply transferring. Because if bioreactor, what will they do? They will absorb the material and simply they will store in their enzyme. Now in their body. In case of adsorption, simply what will act? The your pollutant particles will get transferred from the liquid phase to the solid adsorbent. Now here you are facing that adsorbent that is unreactive. Once the adsorbent is used, they are useless, or they have to regenerate, which will add extra cost to the process. If your industrial application you will set up, that will what leads to extra cost. Now in order to avoid that one, in order to decrease the extra cost, you have whatever the cost you have extra you are giving in our industry purpose for industrial wastewater treatment. Now that extra cost will be reduced by means of photocatalysis. This photocatalysis, what will do? It will do what? Simply the convert the pollutant, organic pollutant or whatever the metallic inorganic pollutant also, they will convert. In case of organic pollutant, they will convert into simply CO2 and water and intermediate product, which will harmless. Which is, what are the harmful pollutants will get converted into harmless compounds like CO2 and water. These are the harmless compounds. No doubt CO2 is a pollutant, air pollutant, but it is a food for the plants. That's why some books are writing that CO2, if at all in industrial area, that CO2 may be pollutant. But in case of your normal village area, that CO2 is not a pollutant, because the CO2 is a food for your plants. We cannot consider that as a your pollutant. Some books is written like this. Now coming to the point, the photocatalyst. When you now I have told the importance of the photocatalyst. Now photocatalyst you are doing. Now photocatalysis are also different methods. Heterogeneous photocatalysis and homogeneous photocatalysis. Now heterogeneous photocatalysis in the means the phase is different. Means you are taking the solid photocatalysis. And homogeneous photocatalysis means what you take the liquid photocatalysis. But liquid photocatalysis, when you are taking, what will happen? That ions also, suppose FeSO4, that photopentant process. Photopentant process in the sense, what is the difficult again? Because the photopentant process, that iron content will again increase in the water. and that iron also you have to remove, because that iron, certain quantity is required for our body, but more than that, that is useless, and that water again polluted. So that we are moving towards the solid photocatalysis. Now coming to the point, solid photocatalysis. Solid photocatalysis also they are using many more applications they have got, but when they are using solid photocatalysis, fine particles are using, because TiO2, the titanium dioxide nanoparticles, they have developed different process for nanoparticles. But nanoparticles are mainly what are the adsorbent, even though, because why you are using nanoparticles or nano adsorbents? Why? Because when you are using nano adsorbent, the surface area will increase, so that the reaction rate will increase, and you will get the maximum removal, percentage removal, or maximum degradation in case of photocatalysis. Because in case of photocatalysis you will call it degradation, and in case of adsorbent you will removal. Now coming to the point, this will, whenever using the fine photocatalytic particle, no doubt it is beneficial. Fine photocatalytic particle is beneficial, but it will create a major downstream process, downstream difficulty. What is that? That is what slurry problem. Because once the water is treated, and that slurry will react. Slurry you have to separate from nanoparticles from the water is a headache, because you have to high capacity centrifuge is required, and which is again extra cost to the water treatment plant. Next, another sense is that whenever fine particles you are taking, that block the surface of the UV lamp, and that UV lamp rigorous cleaning you have to require, because whenever you have handled the fine particles itself, but the TiO2 nanoparticles you have handled. When you are handling that one, what will happen? That simply they will make a layer on the surface of the glass, and by rubbing you have to remove, or else by what your that is sonication you have to do for removing that particles. Means how much difficulty you are facing when you are doing the fine photocatalyst particles. Now, in order to avoid these difficulties, we are developing a catalyst, so that you are making the advantage of your adsorbent, your suppose that technology also developed, like that photocatalyst particles are supported on the inert material, like glass beads or any silica gel, all these things, where they are coating on that by different methods. The different methods, the vapor decomposition and thermal impregation, and different methods are there for impregnating or for coating on this photocatalyst material on the surface of the inert material, or the coarser material they are taking, that is silica gel, all these things. Now when they are taking that one, the efficiency is gradually reducing. Definitely, because whenever fine catalyst particles are taking, efficiency is higher, but fine particles are not taking they are simply coated on the surface of the silica gel, means what? The efficiency will decrease. Now in order to increase the efficiency, what you are doing, the silica gel you simply replace by your activated carbon, that to granular activated carbon. And that granular activated carbon you are simply what? You are coated, even you are place layer, not a layer. If coated means what? The adsorbent is useless. When you will coat this material on the surface of the adsorbent, because adsorbent is inside the photocatalyst. Now how that is useful? Because when a coating will make, that coating will not, what they will do, simply when you are preparing the water material, at a particular place they are coating, because you are retaining the characteristics of both adsorbent as well as photocatalyst. Now it will act like both adsorbent as well as photocatalyst. That's why it is called integrated photocatalytic adsorbent, IPCA are calling. Now this IPCA, various adsorbents are nowadays, the adsorbent are different types of adsorbent you are taking, like zeolite, activated carbon. All other adsorbents are coarser particles, because they are moving towards the coarser particle. Why? Because to decrease what are the downstream disadvantages what are there in the catalyst, and while using the fine photocatalyst particle, again only adsorbent. Now this is our phenomena. And now this why you are using fluidized reactor? Because fluidized reactor, maximum reaction rate or maximum contact between this phase material, or contact between the solid and liquid phase will takes place. Again it will increase the amount of dissolved oxygen also. Now, why use this air also? Why air is required for photocatalyst? From basic mechanism of photocatalyst, what is that? Here, when you are using the photocatalyst, what will happen? These photocatalyst particles, your valence band and conduction band. Now, this valence band and conduction band, when the any light source, UV light source or visible light source or sunlight will fall on the surface of the photocatalyst, like TiO2, ZNO, all these things, MnO2, these are the different photocatalysts. When you fall on the surface of the photocatalyst, what will happen? The electrons will get transferred to the conduction band, and here you will create H plus ion hole and E minus. Now, this is temporary. When you remove the light, again the electron comes back to the valence band. That is called recombination. And this in order to avoid this recombination, because when recombination will occur, what is the use of the photocatalyst? Now, in order to decrease the recombination, what you add? You add air. You are using the air. You are bubbling the air or dissolve. You increase the dissolved oxygen of the air with the water, so that air will be get absorbed by the photocatalyst, and this air will react with your electron. Will absorb the electron to convert into peroxide radicals. Again, this peroxide radical will react with water to form a hydroxyl radical. This hydroxyl radical is a powerful radical. This is because this is important. Hydroxyl radical is in the photocatalysis. Even if any advanced succession process or even if any photocatalysis process, this hydroxyl radical is important. And this hydroxyl radical, what will happen? It simply convert the organic pollutant into what? Carbon dioxide and water. Now this is the role of oxygen, because oxygen will react with the electron to what? Again, hole will remain. This hole, what will happen? The water, what is the water molecule? Present in the solution. Because water you are taking, water. That water molecule, what happen? Will react with the hole to get your hydroxyl radical. Means the hydroxyl radical production is increasing, and this hydroxyl radical simply will organic pollutant or inorganic pollutant, it will convert into CO2 and water, so that the complete degradation of the pollutant will take place. Now, in case of organic pollutant, complete degradation. In case of inorganic pollutant like chromium, all these things, lead, all these things, they will change into that harmless valency. They will convert what are the pollutant valency, they will convert into harmless valency components. Got it? Now, this is for this reason you are using this is the basic funda of your photocatalysis. Now, what is the use of air? You have told. Why you are using air? Because 3 phase because photocatalysis purpose 3 phase only required. Other type of fluid you cannot use, because air is anyhow must required to decrease the recombination rate. Now, coming to the point, when you are using this activated carbon support, some literature I am finding that this will decrease the band gap or band gap tuning. You change the band gap of the photocatalyst, so that the electrons can easily jump from the conduction band to the valence band to the conduction band. Now, the further purpose also activated carbon will add some added advantage to the photocatalysis. Now this is my basic concept which I have used in this concept in your photocatalytic reactor. That is your liquid velocity is 0. When you are increasing the liquid velocity slightly, because this is 0 is indicating. Now, when you will increase the liquid flow rate, what will happen? The movement of the particles will take place. You can see here no movement, because liquid velocity is not changing. Here occasionally the particle air is coming, because that you will creating the bubbles, and the small bubbles will not getting the chance, so that they will small bubbles make a great bubble, and they are coming out of the bed. Now, when you increase the flow rate, the bubbling will be easier, so that at that time no disturbance will take place. Now, coming to the point, when you increase the flow rate again to 5, like you can see the slight lifting of the particles will take place. Slightly the lifting of the particle will take place and start lifting. Here the bubbles creation is increasing nowadays, because initially large bubble is coming. Now gradually what the bubble number of bubbles is increasing, and that is not a constant supply. That's why it is a problem. Now coming to the point, here the bed heights gradually increase. You can see when you increase the flow rate again. Again you can see the particle. Now the air is getting more energy to come out. That's why it is again helping for increase the bed height of the material. Get it? Now the bed height is here, the lighter here, this is the lighter particles. Now this height you have to measure, because gradually you can see the height is increasing. Now you have to note down for different flow rate. Different flow rate, what is the here the fluctuation of the pressure drop also we are finding. Here what will happen, once minimum fluidization is coming, the pressure drop is constant. The pressure drop is constant. Why? Because the low, you can see when 10 and 15 when you see, we can see that this height remains constant. Why? Because there is no change in the pressure drop. Now when I will increase further the flow rate up to 10 LPM I have got. Now you can see when you have 10 LPM, what will happen? This because now fluidization has started. Because the fluidization will start means what? The particle is rising and coming back. That is uniform settling velocity. Because the equilibrium the terminal settling velocity means what? The total upward force equal total downward force. That means at that time the particle will move with a constant velocity. Again it will falling back with the action of the gravity. Now like this, that is settling velocity. That is whenever that is falling back with a constant settling velocity. Am I correct or not? The falling back velocity is not a constant settling velocity. Now likewise the bed height is increasing. Now you can see air velocity and water velocity are increasing. The what? Maximum what? The rotation of the particle will take place. Now when maximum rotation of the particle will take place, maximum contact with your UV light will take place. When you are applying this photocatalytic application, this maximum contact with the catalyst particle will take place. Correct or not? Now, so for that 3 phase is required, because whenever this air also coming, this air bubble also coming means what? They will increase the dissolved oxygen concentration. Increase the dissolved oxygen concentration, so that amount of dissolved oxygen increase and photocatalyst rate will increase. Now this is my hydrodynamic study. Now when you will go for your photocatalyst reaction, first of all only those who are wearing the glasses or that watch glass googles are there, you can wear that one, then you observe the UV lamp. Got it? Now when you are using this UV lamp, total dark you have to make, because outside light also sometimes announce the photocatalytic reaction. Only the UV light will affect or not. That you are checking that one, outside light you are switch on. But now I am not doing that one. Here this simply you are checking that how the color is changing. That you will make. Now you can show this one, that because always you have to maintain above the fluidization, so that the particle will always you have to above the fluidization minimum fluidization velocity, so that maximum particle will comes in contact with the light or light source, so that because the photocatalyst is occurring on the surface of the catalyst. When the surface of the catalyst maximum light exposing, maximum exposure toward the light will take place at more than minimum fluidization velocity. That you will maintain. You can see the bubbling are coming, bubbles are coming, which will increase the amount of dissolved oxygen in the water, and gradually when you increase the flow rate or flow rate of the gas, the particle will comes into, you can see more number of particles. When you will more than that minimum fluidization velocity, when you will maintain, what will happen, more particles will comes in contact with the light source, so that maximum pollutant removal. You can see gradually the color of the solution is changing, because this absorption and photocatalysis simultaneously is taking place. Am I correct or not? Simultaneously taking place, that so that the maximum removal percentage, maximum degradation efficiency will achieve. Now you can see initially the color is gradually decreasing, and that where the color is going on, the color is simply converted into carbon dioxide into water. Got it? This air velocity is difficult to go totally. Okay, like you can see maximum particles are comes in contact with your that UV light, so that the reaction is going on. Now gradually the color of the water will change. Now it will take time, that factors are there, like catalyst loading and effect of air flow rate, effect of liquid flow rate, and effect of initial concentration of dye. Different initial concentration you can change, and your what different initial concentration you take, then your effect of contact time or degradation time. These are the different variables or parameters you have to study. Now coming to the point, kinetics. Here both absorption and photocatalysis is taking place, means your absorption kinetics also you will study, and degradation kinetics also study, photodegradation kinetics. Now for absorption kinetics study, simply you are going for your first order and second order kinetics, pseudo first order and pseudo second order kinetics. Now coming to the point for photodegradation kinetics, Langmuir insulated kinetics. Langmuir insulated first order kinetics we have to study. That kinetics part, next isotherm study also will make, and isotherm also similarly Langmuir, Temkin and your friend with isotherms. Now similarly for here only for photocatalysis only degradation study, degradation kinetics you will study, because adsorption isotherm that is for only purpose for adsorption. For photodegradation only Langmuir insulated equation you are using the Langmuir insulated equation kinetics, and that is for that to first order. That first order kinetics you are applying. That depends upon the different material, because whether it is a second order kinetics or first order kinetics, generally in our cases first order kinetics you are getting, and in case of adsorption you are getting second order kinetics. Now these are all about how you are taking how you are taking the different parameters and different photodegradation kinetics and adsorption isotherms. That too, these are the complete setup of a fluidized photocatalytic reactor. Now any doubt, any questions you are having? Any questions? Okay, now this is all about your fluidized photocatalytic reactor. Got it? Thank you.